let us apply what we learned about the electric field of a ring of charge. And this is example 2. So example 2 states that we have a ring of charge of unknown charge and unknown size, but we're told the strength of the electric field at 2 points on axis. At a point that's 5 centimeters away, the electric field strength is 380 kilonewtons per coulomb, and at a point that's 15 centimeters away, the electric field strength is 160 kilonewtons per coulomb. So the question is for us to figure out what the radius of the ring is and what the total charge on the ring is. So we start with the expression for the electric field that we derived for on axis away from a ring. And that was, this is going to be KQ times X over, I had R to the power third in my expression, but this is also x squared plus a squared to the power 3/2. And that's because x squared plus a squared is going to equal the distance from the periphery of the ring to any point on axis. So this is our expression for the electric field on axis from a ring. And now we're actually given what the value of the electric field is at one point and then at another point. So what we can do is we want to get rid of as many of the things in common between the expressions for the electric field at these 2 points as possible. So we have that, let's see, let's write them out for clarity. E1 is going to equal to KQ x1 over x1 squared plus a squared to the power 3/2, and E2 is going to be the same KQ, the same total charge on the ring, times x2 over x2 squared plus a squared to the power 3/2. So there's lots of similarities between these two expressions. So what we can do is we can actually ratio them to solve our problem. So we form the ratio. So E1 over E2 is going to equal, now the factors of KQ will cancel. So we'll have x1 over x2. And then we'll have, on the top, we'll have x2 squared plus a squared to the power 3/2. And then on the bottom, we'll have x1 squared plus a squared to the power 3/2. So let's see, we know these quantities, we know these quantities. We can't quite figure out what these are because we don't know A. But the neat thing about ratioing these equations is we got rid of an unknown quantity here, which is Q. So we now have one equation and one unknown. We can solve for it. So the rest of it is really just trivial algebra. So what we can do here then is we can move all the known quantities on one side and leave all the unknown quantities on the other side. So now we have E1 over E2 times x2 over x1 equals x2 squared plus a squared over x1 squared plus a squared to the power 3/2. So we can take the 3/2 root of these expressions. So then we find that E1 over E2 times x2 over x1 to the power 2/3 equals x2 squared plus y squared over x1 squared plus, sorry, not y, a squared. So now, rather than dragging this onwards, what we're going to do is, all these things here are known. So we're just going to know this is going to be some sort of constant. I'm going to call it B, capital B. So then my expression simplifies greatly. I have B times x1 squared plus a squared equals x2 squared plus a squared. And again, our unknown here is only A. So I can put all factors that contain a on one side and all the other ones on the other side. So then I get that a squared times b minus 1 equals x2 squared minus bx1 squared. So this expression follows from that part there. So now everything with a is on this side, everything that doesn't have it, everything here is known. So then we get that a squared, or we should just say a at this point, because we'll take the square root, is going to be x2 squared minus bx1 squared over b minus 1. So we know x2, we know x1, b we also know because we know the electric fields and the ratio and x2 and x1. So at this point, really just a matter of calculations. For example, we know that b, given what we know in the problem, is 380 kilonewtons per coulomb over 160 kilonewtons per coulomb. So that's E1 over E2 times x2 over x1 times x2 is 0.15 meters and x1 is 0.05 meters. So B itself evaluates to 3.7. That's B. All right, so that's B. And then we have x2 and x1. So we can plug these numbers in, and we get that A ends up being 7.0 centimeters. So we have figured out what the radius of the ring is. It's 7 centimeters. And lastly, we asked to find what the charge on the ring is. So for that, we go back to this expression here. Or actually, I should say, let's just go to this expression here where we have the numerical values. So forget this one. But now we have x1. We also found what A is, it's 7 centimeters. We know what E1 is, so we really just have to invert this and find what the charge on the ring is. So if you were to solve this, you get that the total charge on the ring is 5.4 times 10 to the minus 7 coulombs. Et voilà.